Now we go to the first speaker. It is Dennis Roskosch. He is at ETH in Zurich, and he is there a senior researcher and doing thermal energy processes. So Dennis, the floor is yours.
Yeah, thank you very much, Corin, and in particular for thank you very much for having me. And yeah, so today I would like to present our study on CO2 neutral process steam, model-based analysis of technologies and strategies. So that was the starting point of our study, the steam supply at industrial sites and the question of how to decarbonize the steam supply. So when we talk about renewable energy and decarbonization, we usually start with renewable electricity, and starting from electricity, various conversion routes to heat are discussed and available. So maybe mostly discussed is direct heating by using heat pumps and electrical heaters like electrode boilers, and also the route over or through direct through hydrogen, by direct combustion or combined heat and power plants. And these are also the routes I would like to compare today. And so I'm sure that you all have a feeling for which is the most efficient route if I would like to transfer electricity to heat. But actually, it isn't that straightforward, because these technologies have different properties or features beyond exegetic efficiency, like economics and feasibility, for example, maximum temperature, and also flexibility. And we would like to cover these trade-offs with our study, and we do this by a system analysis. So what we do is we bring these technologies to the system level and evaluate their performance within the entire energy system. And what we of course need is we need the specification of the technologies to account for them on the system level. And here, a problem pops up, because at least some of these technologies are not market ready, and that means we can't just open a catalog and get the information we need. And we solve this by modeling these technologies. So we take a look into the future and look how these technology can perform in future. And that is what you can expect from my talk today. We first model the technologies, and I will focus here on the heat pumps for a good reason. And then we go to the system level and evaluate the performance of these technologies. Okay, what's our playground? Our playground is a chemical park. And in our world, as engineers, a chemical park usually looks like this. On the right-hand side, we have demands, in that case, time-dependent demands of electricity, 6 bar steam and 31 bar steam. And there is a energy system that currently provides these demands, which is based on natural gas, and it's a large system. It consumes 5.4 terawatt hours per year natural gas, and just for comparison, Berlin needs 5.5 terawatt hours per year for domestic heating. And so what we now do is we keep the demands here on the right-hand side, but we kick the fossil-based energy system, and we aim to replace it by a new energy system based on alternative technologies with the potential for decarbonization. And we also keep here in this study the centralized structure of the energy system, and that means there are no backflows from the chemical park, no waste heat backflows. The only things that are available for the energy system are river water, electricity, and hydrogen. Okay, so before we can tackle the energy system, as I said, we must take care of the heat pumps. And we consider different type of steam generating heat pumps in different or under different conditions, like steam pressures and temperature of the river water and so on. And we also screened for each of these processes and conditions 457 refrigerants. And we do this in thermoeconomic process simulations, where we come from thermodynamics, go to sizing and design of the components, design of the processes, and the processes then always also optimized regarding the COP. And what we then get is a long list of investment costs and COPs and so on for each refrigerant in each for each working condition. And then we discarded some refrigerants, for example, due to too high global warming potentials. And in our study, we finally consider the process and with the best performing refrigerant. Okay, so as I said, we consider various types of steam generating heat pumps. First of all, the direct evaporation heat pump in the basic principle for component cycle as simple as possible. And we consider this in subcritical and transcritical operation. Second, we also consider flash evaporation heat pumps, where this heat pump cycle or standard heat pump cycle first produces hot water, and then in the flash tank steam is produced. And we also consider this in subcritical and transcritical operation. And finally, also direct evaporation heat pump in subcritical operation with mechanical vapor recompression. And in the process simulations, the flash pressure and also the mid pressure here are optimization variables. Okay, so let's come to the results of the heat pumps. And as I said, we analyzed the COPs and investment costs over wide ranges of steam pressure, steam production capacities, and also heat source temperatures. And we will later, or this is all included in the energy study, but here I will exemplarily show some results from these cases. And these are the results for 4 steam pressures, 0.2 bars, 1 bar, 6 bar, and 31 bar, which are relevant for the energy system we consider. And exemplarily, the specific investment costs for a 25 megawatts heat pump. So when we start with the subcritical and transcritical heat pump in direct operation, here subcritical in blue and transcritical in red, we see that the subcritical cycle outperforms the transcritical cycle. So the condensation better fits the evaporation of water than a supercritical isobar. And we directly see that these cycles are able to provide steam up to 6 bar. The transcritical goes up to, I think, 18 bar in our study, but these cycles cannot provide steam directly at 31 bar. If we also then also consider the flash evaporation heat pumps, here the circles, we see that these heat pumps achieve lower efficiencies in terms of COP and higher investment costs. That's mainly due to the flash tank. I think that the efficiency is lower is from a thermodynamic point of view somehow clear, because we first produce water at a higher temperature and higher pressure than actually needed, and then throttle it, which causes usually a high exergy loss. And the process that outperforms all other processes, at least in efficiency, is the combination of subcritical and mechanical vapor recompression, here shown by the triangles, but it comes at higher costs. And if we go a bit more into detail, we see that the efficiency or the COP of the recompression process is also a function of the mid pressure that is between the heat pump and the recompression unit. And the COP increases for lower mid pressure. So in that case, the subcritical heat pump produces steam at 20 kilopascal and then enters the recompression unit. And here the subcritical heat pump produces 6 bar steam, and then it is compressed to 31. So the point is simply the subcritical heat pump, or the heat pump process itself, works at better, it's much better conditions if we produce low pressure steam, and we can also find very efficient refrigerant for these lower temperatures. So what we generally see here in this plot is that there are interesting trade-offs between COP and costs, and that is what we would like to analyze on the system level. Okay, then let's go to the system level, and starting from the demands that we kept and took from the chemical park, we developed a superstructure of the energy system. And yeah, we first have our heat pumps, but we discarded the flash heat pumps because they are more expensive and less efficient. So we do not expect that these come out. And so we have subcritical and transcritical heat pumps on the 6 bar line in direct evaporation, but these processes cannot provide 31 bar steam directly. And we have the combination of subcritical and mechanical vapor recompression. And as further electricity-based technologies, we consider electrode boilers. And on the hydrogen side, there are hydrogen boilers, simple boilers, and a hydrogen CHP that incorporates a hydrogen gas turbine and downstream boilers that use the exhaust gas to produce steam. And the CHP is designed to directly provide steam at 6 bar, 31 bar, and of course also electricity. And as streamline connecting technologies, we consider single recompression units, and in the other direction, throttles and also expanders. And all these components can be built in the energy system optimization. Okay, so it finally ends up in a structural and operational optimization where every technology is characterized by its capacities, efficiency, also part load behavior, investment cost, maintenance cost, and lifetime. And the objective of the optimization is minimizing the total costs while the demands have to be fulfilled. And in the end, the optimization answers the question of what is built, how many and how large, and how is operated. And later we will also vary the electricity cost and the hydrogen costs. Okay, let's start with the first results for the energy system. And we start with the base case. And here we took electricity and hydrogen prices from 2021. And what we see in the result is that the energy system is dominated by large capacities. Here, these are the capacities of highly efficient heat pumps. So mainly the combined cycle is chosen. It is the most efficient, but also the with the highest costs. Yeah, and then we see a transcritical heat pump which is less efficient but also cheaper. A bit of electric boilers, and a small hydrogen boiler, and a throttle is built instead of an expander. And we can have a look how these processes are operated. And the plots here show the steam production in megawatts over time for the typical days that are considered in the optimization. And yeah, it gets clear that the combined heat pump of subcritical and vapor recompression here in gray provides the base load, while the transcritical heat pump is used to provide medium load. It has less operation hours in that case. And hydrogen and electric boilers here in orange and green are only used to cover peak load. And the same is true for for the throttle. So the conclusion for the electricity and hydrogen prices considered in the base case are completely clear. Yeah? A heat pump dominated energy system yields lowest cost. Yeah? But the problem is we have to start the transition of these systems today, but it's uncertain how the electricity prices and hydrogen prices will change in the future. And in the end, yeah, we have to bet on how the prices will evolve, and we have to do this today. And to solve this uncertainty, we varied electricity and hydrogen prices and derived different cases for the structure of the energy system. And first we have the base case. That's the structure you already know. I presented the results, heat pump dominated. Then we consider another case. It's the same structure, but the assumptions are worse. For example, for the heat pump, CUPs are more conservative. And third, we consider a structure that comes out when electricity is very cheap, and another structure that turns out when hydrogen is very cheap. And so what you can see here is the installed capacities. And so we see here we are dominated by heat pumps, here a bit less, but still dominated by heat pumps. And in that case, no heat pumps are built, only or the base load is provided by electric boilers. And here the base loads are provided by hydrogen technologies, in that case, mainly the CHP. And now we fixed the structure of these four energy system and varied electricity and hydrogen prices. And then we compared the total costs of each case for the respective combination of hydrogen and electricity price, and compared it to an energy system which is optimal for this combination of prices. And in the end, it is we made the decision today for the energy system and compare it to perfect foresight. And this is what we get. Yeah, the color code represents, so we have the four cases, and the color code represents the relative cost increase over lifetime. And these are forecasts for electricity and hydrogen prices in 2030, 40, and 50. And we directly see that we are well positioned with the heat pump dominated case here. Yeah, nearly everything is green. Only minor cost increases are expected for all probable price combinations. However, for the electrode boiler system, larger cost increases are expected here. If we had bet on these systems, we had to cope with larger cost increase, because electricity will probably be never cheap enough so that electrode boilers or a dominated system will be cost effective. And for most price forecasts, a hydrogen dominated system results in significantly increased cost. Only if really the lower price limit in 2050 can be reached, a hydrogen-based system could be cost effective. Okay, so that was our starting point, how to decarbonize steam supply at industrial sites. And we saw for the base case that highly efficient heat pumps are favored, and they may cost something, and that's the good news for the manufacturers. And we found that actually the best heat pump is, the best high temperature heat pump is the low temperature heat pump, because it's a combination of a low pressure steam producing subcritical heat pump and mechanical vapor recompression. But there's also a need for less efficient and cheaper heat pumps to cover medium load. And boilers, and in particular hydrogen boilers, are exclusively used to cover peak loads. And then we analyzed which technologies we should bet on today to be as well positioned in the future, even when electricity and hydrogen prices change. And we clearly saw that a heat pump dominated energy system is most robust, at least until 2050. So I would bet on heat pumps. So thank you very much for your for having me, of course, and I thank my co-authors and the funding agency. Thank you very much.
Thank you very much, Dennis, for this very nice introduction and modeling into this field of steam generating heat pumps.